considering how a salt might affect the pH of water, for example, we're going to look at some guidelines for that. And the guidelines come from understanding what a strong acid is and what that means about equilibrium and what a weak acid means. So for a reaction to run in reverse, it must come to equilibrium. And so if we understand that, then this analysis should be a little bit easier. So the guidelines for how a salt affects the pH, we're just going to look at the anion, or the conjugate base of an acid. So the conjugate base of a strong acid will never affect the pH. So I've listed chloride, nitrate, bromide, etc. And because the intact molecule, when it's dissolved in water, we have 100% dissociation. This reaction goes completely to the right. That means the chloride ion is never going to react with an H plus and proceed in the reverse direction. So chloride in the presence of water will never behave like a base, even though it is the conjugate base of HCl. So when we're looking, for example, at sodium chloride, which we'll do in a few minutes, if we analyze just the chloride, we have to ask ourselves, is this the base of a strong acid or a weak acid? And since it's the conjugate base of a strong acid, we know that this reaction will never proceed in the reverse direction. So along those same lines, the conjugate base of a weak acid will make a solution basic. So from our earlier discussion of conjugates, the weaker the acid, the stronger its conjugate base is. And all that has to do with is where the equilibrium lies in that dissociation of the acid. So there is no equilibrium constant for a strong acid. I put infinity here as the equilibrium constant, but that doesn't make any sense. Infinity means this reaction goes completely to the right. So a strong acid will have no equilibrium. So the conjugate base of a strong acid is very, very weak. That's why it will have no effect on the pH. Chloride is very happy like it is, and it's never going to react with a proton, either from a water or anything else, to form the intact HCl molecule. If we look at a weak acid, hydrofluoric acid, its Ka value is approximately 10 to the minus 4. So that means most of this molecule stays intact. And having a hydrogen in the molecule does not make it an acid, but having a hydrogen that dissociates from the molecule is what makes a solution acidic. So when this reaction proceeds, it proceeds mostly to the left because this equilibrium constant is so small. So the conjugate base of a weak acid is going to be a better base. So the stronger the base, the weaker the acid, the stronger the conjugate base. And the stronger the base, then the more basic it will make a solution. And then just for reference, I've got another acid which is even weaker than hydrofluoric acid. So its equilibrium constant is 10 to the minus 10. So this reaction barely goes to the right. It mostly lies to the left. So the hydrogen cyanide molecule, its dot structure looks like this. Only a small percentage of that molecule breaks apart to form the acidic proton. So cyanide, because it's the conjugate base of the weakest acid here, it will behave like the strongest base in water. Okay, so the effect of a salt, we're going to have to remember, we're not going to see an acid or a base. We'll see a salt in the form of a metal and a non-metal. So sodium chloride, the effect of a chloride on the pH would be none, because chloride is the conjugate base of a strong acid. So that reaction will never run. This reaction won't proceed. Chloride in water will still have chloride and water. If we look at sodium fluoride, the effect of the fluoride on the pH is that is the conjugate base of a weak acid, so this fluoride ion is basic. It will make a water solution be more basic. So the fluoride ion, in the presence of water, this fluoride will pluck off a hydrogen off of the water molecule. So remember, when water is in the presence of a base, it acts like an acid and it'll donate a proton. When it donates a proton, we have the intact hydrogen fluoride molecule. This is not acidic. This is just a molecule. So the conjugate base of a weak acid is going to leave behind a hydroxide. This actually came from the water molecule. So conjugate base of a weak acid is always going to make the solution basic. Again, this is just an intact molecule. It doesn't have any effect on the pH. And if we look at cyanide, if we put a salt, for example, sodium cyanide in solution, the cyanide ion is going to be a stronger base than the fluoride ion because hydrogen cyanide is a weaker acid. So everything that we're talking about comes from understanding equilibrium and which direction the equilibrium is favored. So because hydrogen cyanide is a very, very weak acid, that means the cyanide ion in the presence of H+ prefers to make the intact molecule. So if we put cyanide in solution in the presence of a salt, that cyanide ion will react with water. Again, that will pluck a hydrogen ion off of water, make the intact HCN molecule, and leave hydroxide behind. So when we're looking at a salt, we have to be very clear on what a salt is. So a salt is going to be a metal, cation, and a nonmetal anion. And when we're analyzing this, the nonmetal anion, we're going to ask if it's the conjugate base of a strong or a weak acid. So that's really what determines how that negatively charged species, whether it's a cyanide or a chloride or a nitrate, how would that negative ion affect pH? So we go back to the conjugate acid base idea.